afternoon, everyone. This is Courtney at ISPE. Welcome to this month's First Friday webinar. I hope everyone had a wonderful Thanksgiving. Just a couple of reminders before we get started. You all should have received a link to the quiz and the handouts in the email that you received from me with the link to finish registering for the presentation today. If anyone needs help accessing those, please let me know. Please make sure you complete that quiz no later than Sunday evening. PDH certificates will be mailed out within the month, and again, if you have any questions about those, please let me know. Today's presenter is Mark Jers with ADS, and with that, Mark, I'll go ahead and turn things over to you.
Thank you, Courtney. Good welcome. Good day to everybody. Happy Friday afternoon. Hope you guys are all doing well. Again, my name is Mark Jers. I'm one of the field engineers here in Illinois with Advanced Drainage Systems, and I've been with ADS about 10.5 years, and truly do love stormwater. And I think what we're going to be talking about today should be of interest to everyone, even if you're not a designer in the stormwater environment. This initial slide kind of depicts the way stormwater really works and how we in the industry are having to deal with it. You have a traditional stream or creek or river that drains to a larger river, and in that stream or river you have areas that are wide that have really slow flow. There's other areas that are narrow channels that run very fast. You also have eddies and currents that might actually take you backwards. And so in stormwater, it's not always a simple path to the end goal. Regulations and ordinances and other specifications and industry trends have really changed the way we think about stormwater, and it's no longer just a foregone conclusion that, well, you just have it, we'll deal with it, but it's becoming a very important part of site development, whether it be a commercial development or if it be a highway for that matter, a road extension or something along those lines. So what we'll be talking about today is really focusing on some of the stormwater challenges and the options that we have in the marketplace, primarily focused in urban environments. In rural areas, it's a little easier to deal with stormwater. Land is inexpensive. You don't have utilities in the way. You don't have a whole bunch of homeowners or entities to have to try to negotiate the utilization of stormwater management in your system. So kind of as we kind of think about where we are today, our climate has changed dramatically over the last 5 or 10 years, and existing models of design for how much water is falling over what period of time has changed. And so what we've been seeing a lot here in the Midwest lately is when it rains, it doesn't seem to be that we have a rain once a week and we're good to go. There's a lot of cases where it rains very, very fast for a very, very short period of time. And what that results in is higher peak flows. A lot more water is trying to go somewhere in a shorter period of time. And what that really creates is a challenge of what do we do with all that water. We just can't let it run off the site. In a lot of cases, what we're talking about in a little while, but Chicago, for example, you just can't take it to the street and expect someone else to deal with it. So, as we think about today and the future is how we're managing that stormwater, it's not a choice on what we do with it. We have to do something. A classic example is this is a Twitter feed from the Champaign-Urbana area where this is a Twitter showing that emergency personnel are having to run through a flooded street. And this is a fairly common occurrence in cities that have old infrastructure that wasn't sized for the current level of development that might be in the area, or stormwater regulations haven't been able to keep up, or stormwater infrastructure isn't able to keep up with the redevelopment or the construction within the area. So we unfortunately have a lot of cases where there's too much water for the system to handle. And not only is it just the driving public, but in the case of emergency personnel, having to drive through water is not only difficult, but it's also safety and could be health related. So we have to do something to prevent more and more of these type of situations from occurring in the future. I happen to live in the St. Louis area, so I'm going to show you guys an example of kind of how difficult dealing with stormwater is. Being in the east central Missouri area, I'm familiar with what the rain events are like here. So My apologies for not using somewhere in Illinois, but I'm very near and I know what's going on. It's a mid-state. So if you guys remember, the rain we had in the Midwest in 2015 was kind of a strange year, but it's a great example of kind of where we are today. So this is rainfall totals in the region over a 3-month period of time. As you can see, the May through July of 2015 had tremendous amounts of rain as compared to the averages. And so what that's created is a very difficult environment. You know, this is the rainy time of the year, but when you have rain that's, you know, say 50% more than we normally see during that rainy time, the rivers and streams are full, everything's saturated, and it makes it very difficult for rain to go back down to the ground. Instead, it runs off. So just to kind of depict a little of this in a little more specific terms, in the St. Louis area in June of last year, there was almost 29 inches of rain. And if you look at the chart, there was very few days where it didn't rain, and then you had other days where you had way in excess of what we consider our average rain event. That 90 percentile storm would be about 1 inch of rain. So you look at how many days during that period of time where we exceeded that 1 inch of rain. So as a design engineer or someone who's looking at sizing stormwater systems for a project, how do you deal with situations that exceed those design standards? Unfortunately, very frequently. Then you look at 3 months later in September, we had the exact opposite happen, where you had very, very little rain. So in those days, you had a couple of fairly intense rain days, but generally it was little to no rain. So what we'll be talking about today is a lot about green infrastructure. One of the things about green infrastructure that is used frequently is rain gardens and bioretention cells. Bioretention and perennials and plants and trees that are utilized in those environments need water, but they don't need too much water. So within the same season of our year last year, we had the two extremes. One period of time where they were drowning, and then the other period of time where they were needing water, otherwise they were going to die. We had an additional tremendous rain event toward the end of December of last year, where we had over 11 inches of rain in a period of a week. If you guys remember that, most of Missouri and Illinois faced that. And in that rain event, you had semi-frozen surfaces, so the runoff was higher than normal. You had very little infiltration, plus tremendous amounts of rain in a very short period of time. So we had three very significant differences between these three events. Again, how do we in the industry design for these? It's very, very challenging, and so we have to think outside the box on how we're going to achieve those ends. One last point to make on this is then, if you look June to June between 2 years, you had the exact opposite occur. The June of 2016 was very hot and very, very dry. So you had back-to-back years where how do you know how to design to it? So in this particular June, the plants that need that water to survive aren't getting any water, or a couple of days during that month that had water. The challenge with bioretention in one respect is they're very arid soils. They're intended to drain very rapidly. Unfortunately, the downside of that is if it doesn't get occasional rain, it tends to work against that environment. So what we're going to be talking about today is really what's been used in design today, but more importantly, how are we going to deal with these infrequent, high-intensity, short-duration events? Or how are we going to deal with a changing regulation that requires more and more management of stormwater, mainly from a volume perspective? That's been the trend as of late. So what we're really going to think about is where on a green-gray spectrum are we going to be? Just as a quick definition, gray infrastructure as we know it today is typically what you would think of for a stormwater system: an inlet structure and piping, flare-dense sections, could be even channelized ditches, etc. That's gray. Green is grass, plants, flowers, trees, as well as other methods to mimic a pre-developed condition, so that the idea is to the water not to leave the site. It stays on the site and then has an opportunity to infiltrate down into the ground. So this document that you see here is from the Metropolitan Water Reclamation District of Chicago from it was originally posted in 2011 and then reprinted in 2013. What MWRD did in this publication was talk about how they want to implement green infrastructure more broadly. And they define green infrastructure as several key components. They are permeable pavements, such as pavers, porous concrete, porous asphalt would be three very common methods. Infiltration basins, rain gardens, those two are more traditional techniques of channelizing or holding water in a controlled footprint to give it time to infiltrate or evapotranspirate with plants and the sunlight. What they're also talking about is utilizing storage underneath the ground in stone structures that hold the water in a controlled footprint. They went on to say that what their goal is, as I mentioned a little earlier, is that one of those primary goals is to encourage infiltration down into the groundwater system. And essentially what I would consider that is what we're talking about here is volume reduction. So you have a 1-inch rain on a site. The goal is to let as little of that 1 inch over that surface area from leaving the site. Obviously your goal would be to have zero leave, but often in urban environments that's not practical. So we look for something kind of in between, generally speaking. So finally they talk about, in this particular publication, about some of the things that need to be monitored. Green infrastructure in the Midwest is fairly new as far as a best management practice for stormwater management. And so they talk about, on the next page, which I don't have in this particular presentation, but it talks about things to observe such as maintenance, using the storage in stone, looking at potential clogging if it's not pre-treated properly to ensure that the sediment is removed from the flow prior to entering those porous environments. But they state that the longevity is still in question because there's not enough history in the Midwest. ADS as a national company have seen practices nationwide and seeing some pullback somewhat of traditional green infrastructure because of the lack of maintenance or understanding about the techniques, how they should be used, how we control the volume, changes in the environmental conditions between the summer and the winter, such as 1 month it rains 20 inches and the next month it's 5. So dealing with those sorts of things are still being observed. One of the leading agencies in the Midwest is NEORSD. That's the Northeast Ohio Regional Sewer District. Their director is Kyle. She has been very outspoken about the needs of their market and their area. And what she has talked about is the importance of mixing green and gray in the infrastructure. And the reason for that is because purely gray infrastructure is having a difficult time managing the maintenance aspects as well as these unusual rain events that we've had. So finding the right mix between traditional pipe and structure versus plants and grass and trees, finding that good medium is important. But it's very specific to a site. It's not going to be just one size fits all type of approach. So stepping back a little bit to redefine again, one of the primary methods utilized for green infrastructure is bioretention. There are, again, plants, swales, etc., that use native vegetation, usually with very deep root systems, usually native plants to that area. The other is pervious pavement. Again, there's 3 main areas there. This picture happens to be asphalt. The other 2 main ones are concrete as well as pavers. The idea with these is to capture the water in that surface or over that surface and take it down underground and give it time to control the flow. Stepping back to the challenges that were mentioned by MWRD, these are in urban environments. You have challenges such as not understanding the importance of the environment around that green infrastructure, such as trash, not cleaning pervious concrete or vacuuming it. That's really what you have to do. In arid times of year, the importance of watering it. Like, for example, the top center is a curb bump out with green infrastructure in an island area where they're having to pull a hose across the street to try to keep it alive. In another bump out in that same area on the top right, you see they mowed it down. Someone didn't understand that those plants and what looked like weeds maybe to them were very important. Even the inlet to that area is clogged now, as you can see with that the drop in the curb. In the bottom right, for example, is a maintenance worker with a weed control. Invasive species love fancy soils and lots of greenery and very rich environments. Honeysuckle and crabgrass, poison ivy, those sorts of things love it. So the nut sedge is another. So the idea having to properly maintain it to ensure that those invasive species don't take over and basically just destroy the environment. This picture is an example of what happens when you don't maintain it. This is invasive native species of weeds that have taken over what was a rain garden at one point. And we obviously want to try to avoid this, so regular maintenance of landscaping is certainly very important. This is a photo of a pervious concrete that this was soon after construction. During the construction phase, it was not properly maintained from a SWIP perspective. You know, the sediment control wasn't working adequately. The result of this was when it rained, it flooded. One of the challenges in design with traditional green infrastructure is ensuring that you have proper overflow control mechanisms. You obviously don't want this to happen, so you know, planning for a potential overflow or a lack of maintenance might be part of a standard protocol to ensure that the systems function even if they're not being maintained. Another challenge that we on the design side often hear a lot about is construction staging. General contractors and site contractors talk often about the importance of placing green infrastructure at the right time so you don't have to rebuild it. Normally in a site development or a roadway, you usually put your utilities in first. Your gas, your electric, your water, your sewer, your stormwater, all that's done first. Unfortunately, when you're using a traditional bioretention or pervious pavement, you can't do that because the area ends up getting used as this one has for staging or just trash and limited construction capabilities for that area. So that is a picture during construction, and this one is after. Very little of the original green infrastructure that was planted is there. It's the outlet, you can't really see it there because it's clogged. So the functionality of this particular this cell is pretty much non-existent. A classic example of what can happen if it's not properly maintained is this site here. This is a retail establishment with a rain garden in the middle of the parking lot. So 2 days after it had rained, there was still water in that cell. That's the first red flag that this filter, if you will, has failed, and it's time to regenerate that soil so that it can infiltrate once again. So then I went back 5 days later, and there's still water in it, which is indicated that, and there had been no rain. So in this case, within less than a 3-year period of time, this particular green infrastructure is needing complete replacement. Certainly a red flag that it's a problem even if you don't drive by and do your inspection with an infiltration test. It's like here, you have moss growing in it and you have cattails. Cattails need water. So if you have cattails in a rain garden or a bioretention cell, that is telling you that you need to call out a landscape crew to fix it. So then I went back again, so this is now over a year later to that same site, and nothing has been done. So one of the biggest challenges is compliance. You know, when as there's more and more mandates to using green infrastructure, compliance is very, very difficult. How do you enforce the maintenance and operation of these sites that are intended to clean the water, hold the water, eliminate stormwater from the system? So, you know, even though this is in an area where compliance is required, it's still, the enforcement of that is very difficult. So thinking, why is some of these things happening? You know, why are we seeing issues with pervious pavement or rain gardens not working properly? It's a function of our environment here in the Midwest. You know, this is a picture of a linear rain garden in a parking lot. On the left side is pervious asphalt with basically just stop blocks for the cars that drain water through them. So in an infiltration BMP such as rain gardens, bioretention, or pervious pavement, the drainage surface is the very bottom. So if you look at this box, of the 3 sides that are subsurface, only one of them is an actual infiltration surface. The other 2 are channelizing it. So in these types of environments, if you have clay soils or soils that do not infiltrate well, which happens to be mostly what we have here, most of these sites will have an underdrain in the bottom. So all you're doing in these particular cases is you are slowing the flow up, you are cleaning that flow, but you are really not giving it much time to infiltrate with an underdrain in the bottom of it. What might be a better way to get an infiltration BMP to work is to spread it out. So like in this particular example, you have pervious asphalt on the left. So what you're doing is spreading out that water over a larger area, a footprint, so it gives it more residence area to infiltrate. You still usually need an underdrain because if you don't have that and the soil's not draining, if you have back-to-back rains, your surface is now flooding, and generally there's no overflow in place to handle that. This is more traditional stormwater management. This is a parking lot in an industrial area, and in this particular case you have sheet flow across the parking lot. So it's draining to inlets, it's draining to a curb, and then the water is collected, and then in this particular case it's detained underground, and it gives it time to infiltrate or store it, attenuate the flow until it's time to release it from that site. So what we're going to be focusing on and how to deal with these challenges is using more traditional infrastructure, subsurface facilities for stormwater, and talking about 3 specific ways of doing that. One of them is detention, which is basically holding the water. Retention, which is basically permanently holding water until it's infiltrated. So in the retention environment, your design is set up to not allow any of that water to leave the site. And then there's also a combination of retention and detention in design. And finally, treatment. You see a pervious pavement that's clogged, and the reason why it's clogged is because you have upstream drainage area that's dirty, that's draining to that area. So how do we pre-treat? How do we ensure that the best management practices are sustainable long-term? And the way you do that is through ensuring you have pre-treatment methods in place in order to accomplish that end. So it becomes more complicated is that it's just not as simple as what do I deal with that water, but you have landowners, you have developers, you have a DOT, a city, or somebody else who has a lot of varying interests. If it's a commercial site, they're most interested in having lots of parking. If it's a park, they want lots of green space, but they also need parking. If you're a municipality, you have concerns about what my long-term maintenance cost is. Do I have the crews to do it? Or if it's pervious pavements, how do I deal with winter weather? How do I deal with snow and salt, or can I sand these environments that are pervious, for example? There's just lots of things you have to deal with. So what I wanted to show you is an example here of MWRD stormwater management principles and their requirements. So this is the greater Chicago area, and what they say you have to do on a site design. So basically 3 different types. How do we deal with runoff? How much design do we have to do there? Volume control is basically green infrastructure. How do we eliminate volume from the flow so that that 1 inch of rain that falls, maybe I am only allowed to release 0.3 inches of that 1 inch of rain. And then in addition to that, storage. If you have a condition where your downstream storm sewers cannot accept a lot of water, you have to hold that water. You have to attenuate it and give it time to sit until the rain event is passed, and then it can be metered into the system so that you're not surcharging your existing systems. So for example, if you look at a traditional application for stormwater management, a non-residential environment, you have almost any site has to have all 3 of these, or all 2 of these controls. And certainly if it's a larger site, which a lot of large developments, you're going to have all 3. So a half-acre site's not very big. So if you have a CVS store or Walgreens, or you're putting a new lane on a 1-mile roadway, you're going to fall within runoff and volume control. So like you look at that, at a half acre, you have to mitigate stormwater and reduce the volume. It's very challenging to do, but it's a requirement that is set up by statute. So there's no way to avoid compliance with this. As the urban environment gets more and more expensive, more and more of the stormwater management is going subsurface. Now we're going to talk about a lot of the ways that you can do that and some of the benefits or the capabilities that a subsurface system can do for you. The pervious pavement, one of the green infrastructure techniques we talked about, is a underground solution. So underneath that pervious pavement is a rock base, anywhere from 6 to 18 inches, maybe 24 inches thick. That rock is a clean stone. It has generally a 40% minimum void ratio. So you have the opportunity to store that water and give it time to either attenuate or infiltrate in that environment. Rain gardens and bioretention also fall into that category. These are several picture examples as well as some schematics of how it's accomplished. You know, underneath that rain garden or that linear system, there is either a stone matrix or a stone and or dirt matrix that has a void ratio or a holding capacity for stormwater. So again, this is also an underground because what you're seeing is only the surface, but there's definitely something underneath that that's also managing that water. One of the more traditional techniques in urban areas has been pipe. The most common types of pipe used for underground stormwater volume retention, detention, or a combination thereof is plastic pipe, corrugated polyethylene, or polypropylene, and then corrugated metal pipe is also used fairly frequently. Occasionally, in some markets, reinforced concrete pipe is also used. In very large volume situations, there are vault options. This is this shows an open bottom vault. They can be double stacked or they can be closed. So they can be used for either retention, detention, or they could also, well, pipe could be as well used for rainwater harvesting, so holding the water and reusing it in some other method. There's a whole lot of crate options out there also. Some people call them milk crates. They also have different looks. Some look like these boxes here, but some look like columns of polyethylene or materials such as that. So they basically do the same thing. Crates have very high void ratios. So basically the entire area is available for storage. They are challenged with pretreatment and how you pretreat. There's no way to maintain these types of systems without pretreatment. So there's also no ASTM standards nationally for them. So it's just a matter of whether or not they can demonstrate structural loadings, because these are usually under paved surfaces. What we're going to be focusing on primarily today are chambers. This is a continually evolving method of managing stormwater underground. It's quite intuitive. We'll be talking about that as well. There's quite a few manufacturers on the market now because they're easy, they're inexpensive, they're fast to install. Some of them are structurally sound, so they have the ability to be placed anywhere. So I mentioned earlier that detention is one of the options that we have to deal with. It would be an MWRD, it'd be the far right column. What detention is basically doing is it's taking those large rain events and they are holding them back. So basically the idea is to store the difference between those two curves, the red and the blue curves, so that that water is held for a period of time so that your peak is not running off the site and flooding the downstream. And it truly is, as I showed here, flood protection. It's also scour protection. You know, if too much water gets to the creeks at one time, it's undercutting the banks and causing all sorts of trouble. So this is becoming, obviously, this has been around for a long time, but it's being discussed a lot now. So when we look at how that flow is managed in a detention environment, so you have a series of pipes or some sort of detention method. You have an outlet control structure. That outlet control structure is metering the flow. You usually design it for a low flow, which allows for a certain flow rate out of the system during any rain event. And then there's a weir, usually that has some sort of control mechanism. So you're ponding the water behind that weir for a period of time and a height to control how much volume. This is a picture of a couple of examples. The one on the left has, you can't really see it, but there's 3 inlets into that structure. You have a small low flow orifice that's probably a 3-inch outlet, so very small flows, and then a very tall weir that's detaining a tremendous amount of water, and then a notch for the secondary storm, and then the top edge of that weir would be your maximum design storm for that site. On the right is another simple example. You see the water coming in from the right, it's exiting to the left, and you have a low flow at the bottom and then a weir that controls the high flow. So these are just 2 examples of how that water is transferred through that control structure. Without this, some sites don't have a structure even. It may just be a very small pipe at the outlet. But with that particular condition, if you have one of those high intensity, short duration events with a high runoff, you might exceed the capacity of that outlet pipe, and then you would have significant ponding upstream from even the detention, which certainly isn't desirable. So I mentioned we're going to focus on chambers today, and that's primarily because they are becoming the preferred solution in the industry. So this concept of chambers for subsurface stormwater, for subsurface infiltration, is nothing new. This is how they were initially designed. This is septic systems in rural America. These are everywhere. So what this has is it's all of your plumbing from your home drains to a septic tank. Let's call it your pretreatment. And then downstream from that is your infiltration area. So looking at it from another perspective, you have a septic tank that holds your waste and your solids, your floatables, etc. And then the cleaner water is then distributed to a series of chambers to spread out the water and give it time to infiltrate back down into the ground. This technology has been around way longer than the chambers that are currently being used today for stormwater. The difference between the septic chambers and the stormwater chambers is the septic chambers are not intended for traffic loads, for deep burial applications, meaning more than a couple feet deep. The stormwater chambers are structural chambers intended generally to be under paved areas or areas that may have live loads. And so that's the main difference, but the concept is identical to this. So what is that? Why is that pretreatment important? This is a picture of a pretreatment cell in a chamber that has a woven fabric on the bottom. And this particular picture is a site that had a blowout, a significant blowout of the upstream erosion control. The result of that blowout of erosion control was a tremendous amount of sediment entered that pretreatment cell. What you're seeing here is what the cell looks like after half of it was cleaned. That sediment on the right is 2.5 feet deep. This is the next picture on the right here is the row adjacent to that. So as you can see, all of the sediment was trapped in that first row. So what the chambers can do is store a tremendous amount of sediment in a footprint underground. So this allows for even in worst case scenarios of no maintenance where the system is still functioning under its intended design. Retention is the other method, as I mentioned earlier. Detention is holding the water and releasing it at a controlled rate. Retention is where there is no outlet. In a pure retention environment, water comes in, it fills the chamber system, and then it is infiltrated over a period of time into the ground. That is it. There is no other method for outlet. So when we think about the wastewater septic system that I showed earlier, that is pure retention. The difference between a septic system and a stormwater system is that the stormwater system has to manage an infrequent amount, but a much larger amount. So how we manage that and how we deal with it is very, very different. So what we see more often than not, because in the stormwater environment we have unpredictable storm events. So what we normally design in when we're looking at a volume reduction environment is a combination thereof, such as what you see here. So water comes in, it flows down that pre-treatment row, and then as the storm continues, it fills up to a manifold and then will rapidly fill the system through an outlet. So if you look at the bottom right, that's a schematic of the outlet side. So you do not see a low flow outlet, so there's no pipe at the bottom of that weir. It's only allowed when there's an overtop of that weir. So anything below that top weir crest elevation is infiltrating. Anything over that is detention, so it's holding the water temporarily until the storm event is passed. The beauty of the combination system, like you see here, is you're getting volume reduction. So you're eliminating some of the water that would normally leave the site, like you would see in detention. But it's also holding water for those large events that exceed the traditional water quality events. A classic example of this is in the DuPage County area in Westmont, Illinois. This was a large Mariano's store, and this is just some of the general design criteria. This particular site had a massive detention requirement in excess of 5 acre-feet. So the design engineer in this case looked at a combination of bioswales or a surface B&P feature, and then they looked at what they could do with bioswale, and then said, okay, I have to do something with the rest. So the almost 5 acres was utilizing chambers and storing them under the ground. This is a picture of during construction and also some of the stormwater B&P analysis that was done. As I mentioned, about 1/3 of an acre-foot was used for bow retention, and then the rest of the infiltration B&P was utilizing subsurface storage. So you can see here it's just simply a row of chambers that have an open bottom that allow for water to go down rather than out immediately. There's continually a lot of research being done on this technology because of its value in the marketplace. In Toronto, the Toronto Conservation and Region Authority back in 2010 did a bunch of research on subsurface chambers. They set up systems where they had flow controls on the downstream side of a control structure that was intended for infiltration. They had flow monitors on the inlet side that evaluated how much water was coming in. It's easy to calculate your total volume based on that flow coming in. And the result was that they analyzed how much water over a period of time was being retained. So the rainfall data over the 2 years that they analyzed, it was in excess of 70 rain events that met their criteria. And so anything below the 2.4 millimeters wasn't counted. Those are those very small rain events that you wouldn't even hardly capture on the flow monitoring data. So this is a significant number of data points, so the data is certainly valid. What they showed was that between 80 and 90% of all of the water that fell on that site was retained. And if I could send you the report if anyone is interested to read the entire report, but what they said was that they also had some issues with the weirs at the downstream side where water was bypassing around. So the flow monitoring devices downstream of the outlet were actually picking up water that should not have been picked up. But even with that being the case, the volume reduction was extremely significant. You know, by designing in infiltration B&Ps using chambers, they were able to reduce the volume total by between 80 and 90%. St. Louis has done something similar. They have approved one of the technologies with a runoff volume reduction, which means that they actually accounted as a B&P to reduce water leaving the site. More and more cities are doing this because if you're a combined sewer, the EPA is requiring you to do volume mitigation, basically try to be better than pre-developed conditions if that's possible, to actually reduce the amount of water that's actually entering the combined sewerage system. So in this particular case, what we looked at was a 1/2 tenth per hour of infiltration through which would be a Class D clay soil. And we modeled the ability for water over an impervious area and calculated the area needed to infiltrate. The purpose I'm showing this slide for is that there is somewhat of a diminishing return on the depth of that water column. What we found is that at about 18 inches of water column depth for infiltration, the value of Darcy's law decreases. So basically, the more head that is created, the less value that head has for infiltration. So generally what we're finding is that about 18 inches of water is a good depth for infiltration. Any deeper than that you're really not seeing the value with that. So what we recommend is that you look at it at an infiltration depth of about 18 inches or less. But you could go deeper. It's just you're storing water for a longer period of time and you may not see the end result. Again, the whole idea is to spread it out. So when you look at an infiltration, it's less about a volume than it is about the area you're infiltrating. So oftentimes the idea is to use a smaller chamber like that's used often in septic and use more of them. So you spread the water out over a larger area and it gives more infiltration surface. Very similar to what I talked about in bioretention versus pervious pavement. Bioretention has a small footprint on the bottom, so the infiltration capability is less than pervious pavement with a broader area for infiltration. New York and other larger cities have had to deal with stormwater in interesting ways. This is actually from New York's DEP's manual of stormwater management, and what you see here is a replacement curb with infiltration surfaces like porous concrete or pervious pavements, and what that allows is water to infiltrate down into a chamber that then holds the water. One of the challenges in urban environments with tall buildings is the ground doesn't see sunlight, and perennials that are most often used in bioretention need sunlight. So the success of longevity is very low. So they need other methods to store that water, infiltrate that water than that. This is just an example of how that's being employed out in the New York area. This happens to be a residential, but it could be anywhere. This is a right-of-way example of doing the same thing. I've highlighted in red the 3 infiltration basins. Because these are structural chambers that are traffic rated, you can put them right underneath the roadway, as is shown here in this example. The Washington DOT also has done similar things. What they have done is they have actually analyzed it. You see areas that are offside of pavement on the left, and then under pavement, under the edge of curb on the right picture. This is right out of their best management practice manual for the DOT out there. If you look on the bottom left, you'll see that they do see chambers as a flow control. So you're metering the flow or you're slowing the flow up. You're also cleaning the flow through. They show dissolved metals and solids as well as phosphorus, but they're also showing it as LID, which means low impact development, which is basically green infrastructure. So they see chambers also. So you have DOTs, you have urban environments like New York or cities like St. Cloud, Minnesota, and many, many others that are doing the same basic practice with chambers. So in addition to raw volume reduction or detention, another method of volume reduction is harvesting. There's a lot of methods out there. There's subsurface systems such as Xerxes tanks, above ground systems as you see on the right. They can be under parking, they can be outside of parking, they can have a lot of benefits. They can be used for LID or for lead sites where you're reusing that water for irrigation or for flushing toilets, etc. There's a lot of options out there. The challenge that this particular sector of the lead movement has had is the ROI. You know, like I showed in 2015 summer, you had way too much water for the plants, and so the plants don't need to be watered. But then when they needed water in September, those tanks are empty, so you're using potable water anyway. So it's trying to figure out, you know, how to size them and how to manage that flow is very difficult. The third piece that we need to talk about is treatment. Bioretention and pervious pavements, they are treatment methods. They are not good at trash. They are generally not good in bioretention if you're on sites that have hydrocarbons, but they do a good job of filtering suspended solids, phosphorus, nitrogen, other contaminants such as that. Subsurface technologies are broad as well. There are a host of hydrodynamic separators that are decent at removing sediment and oils and trash. The chambers themselves, as I showed earlier, are very good for sediment, but they can also store trash and other contaminants that are flowing off of a site. Sand filters and other boxes are also methods that can be utilized. The recommendation I have for for treatment is that you size them only for that first flush, for that first part of the storm. If you size them for your major design event, you are making them very large, very expensive, and if the peak flow is exceeded, they'll wash out, and then any benefit they have has been negated. One item that is often not thought about that the University of New Hampshire studied a number of years ago. In 2011, they issued a report that talked about the thermal impacts of various BMPs, and what they concluded in that research was that subsurface is ideal for managing thermal impacts, whether it be hot runoff during the summertime or freezing conditions in the wintertime where you have a frozen surface and you're getting zero infiltration or water quality impact on that surface. So they found that the ability for a subsurface that's always at 55 degrees, it allows for a very consistent performance year-round. It also allows for a cooling of the water because of its thermal lag. It has a fairly long flow path between the inlet and the outlet, so it has time to cool before it enters that stream. We're seeing more and more protected streams throughout the country, so this is something that in the past has never been thought about, but it's certainly a very, very important part of where we're headed. There are a lot of cases where the green or gray is not adequate. So I'm showing you a couple examples here where chambers in this case are used underneath bioretention and rain gardens. So you get your first flush or your water quality storm through the bioretention. You get your water quality or your infiltration through that matrix, and then the chambers are used for the larger volume storms that may exceed that initial design event. Another case is this is with a crate system that it's called rain store that's used underneath rain gardens or pervious pavement. Again, in this case, it's very good. This is a good application because it's not in well, at least in rain gardens, not under pavement, but it gives you a high void ratio. So this would be very good in a linear rain garden application to store water, either to infiltrate it or to detain it. So thinking back to where we started in this hour discussion is our climate is changing dramatically, and how we manage stormwater is very different than it used to be. So it's important to remember that we maybe have to think a little differently. You know, we don't need emergency personnel driving through flooded streets. So how do we mitigate those flood events in urban environments specifically? You know, we have a supercell come over us and it gets 3 inches of rain in 20 minutes. Gosh, how do we deal with that? You know, it's going to be very site specific, but it's something that regulations are going to control, and we're going to continue to see tightening of those, not spreading out of that. So the chambers do an exceptionally good job of that, but again, there's other methods as well. But it's certainly there's a lot of things in your toolbox that you need to consider. So, and it's really, again, 3 pieces of that puzzle. It's you're holding the water, hopefully you're infiltrating that water, or you're giving it time to leave the site or leave through the ground rather than through a pipe. And pre-treatment, again, is very important. You have to, without the pre-treatment technique in place, you are going to have a shorter life or a very high maintenance cost that neither of which are palatable. So that's the end of my presentation for today. I hope you learned something. If you have any particular questions for me, you can always call me or email me or whichever. But I do encourage you to use us in our industry. There's a lot of industry professionals in stormwater management there to serve your needs and help in design and facilitation of your projects.
All right. Thank you so much, Mark. I just received a question. If you don't mind taking a few of those.
Not at all.
All right. So someone asked, how are underground pretreatment chambers efficiently cleaned of sediment and debris? It appears to require manual work in a very confined space.
Sure, that's a great question. So there's the different manufacturers have different techniques. Some of them use a sump system that captures sediment through basically it falls into a sump that's vacuumed out through a vector truck. The ADS technology uses a woven fabric on the bottom of that pretreatment row. It's a double layer of a woven fabric that is accessed through an inlet manhole that uses a jet nozzle. Same technology that's used to clean a sanitary sewer system or a septic tank. They're self-propelled. They run down the row and then they're wenched back. So it pulls that sediment, pushes that sediment back to the inlet, which is where it's then sucked out again through that vector truck. The picture I showed of the blowout of the pre-treatment or of the stormwater inlet control, where it had 2.5 feet of sediment in that row, that was half cleaned. You could see that they started cleaning it on the left side, and that picture was taken halfway through the cleaning process. That jet nozzle had cleaned the left side of that row, and then all that sediment was sucked out by a vector truck. So that method eliminates the need for manned access into that row. Other techniques are using a separator or like a hydrodynamic separator upstream from the chamber system. That separator is going to pull out your sediment and trash. So that's another method.
All right. I haven't received any other questions. So I will go ahead and just ask, if you do have questions, you can either direct those to me and I will make sure that Mark gets them, or I'm sure Mark would be okay if you emailed him directly. So with that, I will go ahead and end this month's webinar. Just to let everyone know, we have started posting the webinars for next year in 2017. So keep an eye out for those. And as always, if you have questions or comments or suggestions for future topics, please reach out to us here at ISPE. With that, I will wish you all a happy holiday season. And Mark, thank you so much.
Thank you.
All right. Goodbye, everybody.